In this video, I want to talk about sampling, and I want to start by looking at ideal sampling. Now, as the name suggests, ideal sampling is a kind of sampling that possibly we cannot ever achieve in real life. But I think there are some advantages of looking at that because you understand what the what is it that you actually want at the output of a ideal sampler, and you start to understand the kinds of constraints that you have to put so that a real sampler can be built. Okay, so let's take a look at sampling. So imagine that you have an analog signal like this. Okay, and you want to sample this signal. What I mean by sampling is I want to take basically the values of this signal at certain time instance and not at any other time instance. So I want an output like this. How do I get this? I simply multiply my signal with an impulse train. Okay, a train of impulse signals or direct delta functions. And what is that? One way to think about that would be just to say that it's a value of 1 at a particular time instant and 0 everywhere else. That's not a mathematically rigorous definition, but I think that would do for the purposes of our course. Okay, so basically what we are saying is that the sample signal, which I have called YA here, is the analog signal xt multiplied by this train of impulses. Now we have looked at this before, but if you look at this entire process, this process of converting from the analog signal xt to the digitized signal YAT, in the frequency domain, you get something like this, right? So you have, if your spectrum in the analog domain looked like this, it was band limited. What you would have is if you sample it with twice, uh, if you sample it such that your sampling frequency is at least twice the maximum frequency in the signal, which here is FM, then you get replicates of this band limited spectrum again and again at multiples of the sampling frequency. We've looked at this already, and I hope this concept is clear to you. And what that means basically is that if you put a low pass filter here, you can actually get the analog signal back. You can recover it completely. So, what I'm saying is that sampling is a reversible process. Or, in other words, sampling is a lossless process. So, when you go from this signal to here, this is lossless, right? Even though there are replicates, these replicates can easily be removed by low pass filtering. Um, and you can see this in frequency domain very easily. But when you look at the time domain, you may think that you are losing information when you go from xt to yat. But actually, you are not if you keep the Nyquist criterion. That is, the sampling frequency should be twice the maximum frequency, at least twice the maximum frequency in your mind, and you sample using satisfying the Nyquist criteria, then this sampling, even though it looks as if you're losing a lot of data in between, you essentially do a lossless transformation. And that's what this frequency spectrum shows us. Okay, now I want to just talk about the fact that ideal sampling is impossible. Okay, um, again, let's think about this sampler here. This sampler is going from this xt, this signal, to xat, which is just samples of the signal. Now, what does that involve? Okay, it involves two things. One, think about this time instant, the time instant at which we are picking up this value of xt. What we are saying here is that we are able to pick up the value of the analog signal x at without any time, okay, in almost like infinitesimally small time. We are able to get the value from the analog signal. Now, as you would imagine and as you would know from your analog electronics, that is impossible. Basically, because what does it mean to get the value of the signal? What we mean by saying we want to get the value of the signal is that we want to store this value on a capacitor or something of that kind, right? Um, However, this storage, if it's a capacitor, means that it is going to take some time. It's not going to happen in an infinitesimally small time or almost or no time. It's going to take some time. So the input requirement, the requirement that we read the input in zero time is impossible. Okay. There's another impossibility in the ideal sampling, and that is an impossibility at the output side. Now take a look at this. What is going to be the output immediately after we have picked up a value? Zero again, right? So what we are saying is, yes, we have to pick up the value of the input signal in zero time, but we also have to immediately lose the entire value immediately. How are we going to do that? And even if we are able to do that, would the circuit that goes after it, and we looked at what is going to go after the sampler, what's going to the circuit that's going to be here is going to be an ADC, right? A circuit that will quantize the sample values. Will the quantizer be able to uh, uh, do the processing of this value or quantize this value in just no time? No, that's not possible. And that's why ideal sampling is doubly impossible at the input and at the output side. And in the next few videos, we'll see how we kind of tweak this circuit a bit to get a more practical circuit.